Welcome to the next video in the course in real analysis. This is lesson number 3 discussing orders. What you can expect to see in this video is a definition of partial order, poset, commensurability, and total order. We'll then see examples and non-examples and exercises at the end. Now, in the previous videos, we've discussed the field or the so-called algebraic axioms, and these are called algebra because they have to do with plus and times, which we often associate with algebra. But in this video, we're going to talk about the less than or equal to symbol, which is to say the ordering on the real numbers. And so here we have the definition of a partial order, right? So the idea, as we have done with other topics, is that I'm going to present this in a very general way, in a very abstract way, and eventually it will get applied to the real numbers. But here's the abstract definition of a partial order. We start with a non-empty set X and a relation on X. Now, it should be familiar from a course in discrete math what it means to be a relation, although before talking about that, I'm going to use this curly less than or equal to symbol to talk about the relation. So it's a curly less than or equal to emphasize that it is abstract, it is related, it is similar to the familiar notion of less than or equal to, but it may not be exactly the same thing. So that's what this symbol is. This is the symbol for the relation. And remember what a relation is. That should be familiar from a course in discrete mathematics. It means that the relation is a subset of the Cartesian product of a set with itself. So that's what it means to be a relation. And again, because I hope that is familiar from a previous course, then I won't explain that any further. But that's what it is to be a relation. What it is to be a partial order on X is that the relation must be reflexive. And reflexive is a property that I assume is, again, familiar from discrete mathematics. It must also be anti-symmetric. Now, anti-symmetric is actually not so common to encounter in discrete mathematics. So I'll go ahead and explain what that means. It means that for any two elements that you choose from your set, if A precedes B, so let me actually explain what I'm saying there. This, because it is an abstract less than or equal to, a nice way to pronounce what it is expressing, basically, is to say that it means A precedes or is equal to B, right? So A precedes or is equal to B. But that's a lot, right? That's, I don't want to have to say that every single time. So for short, I'll say A precedes B. So that's my shorthand for A precedes B or is equal to it. And that is how I pronounce what I'm writing here. So anyway, to get back to anti-symmetry, if A precedes B and B precedes A, right? So the relation holds in both directions. Then A must equal B. This is the property that defines anti-symmetry. So if the relation has this property, then the relation is anti-symmetric. So whenever the relation holds in both directions, it must be that the two elements are equal. That is anti-symmetry. Okay, and then finally, the relation must be transitive. That's another one that I think is so familiar from a course in discrete mathematics that I won't explain that any further. Now, if you have a partial order on X, right? So if the sort of precedence relation is a partial order on X, then we say that the pair of the set together with the relation is a poset, which is short for partially ordered set. And that's a little bit funny because, well, like this is a pair, not a set, right? So why are we calling it a poset? Well, that's kind of like what we've seen when it comes to rings and fields and groups. We're mostly thinking about the set itself, even though part of what defines the structure that it has is the operation in the other cases, or in this case, it's the relation that kind of defines the structure. But in any case, we kind of just linguistically, verbally, we talk about and think about the set, even though this other thing is part of it. So anyway, that's just kind of like, how we tend to speak about these things when we're being just slightly informal. But there you go. That is the notion of a poset. Oh, right. And I wrote out in its own slide what it means to be antisymmetric. So here you have it yet again written out. This is what it means for a relation to be antisymmetric. So let's now look quickly at a few examples. The number examples are all really sort of immediate and intuitive. So if we're talking about the natural numbers, for example, with the standard less than or equal to relation, then this will be a poset. And there's nothing special about the natural numbers. We would get an example for the integers and the rational numbers. Again, the structure of this course is that I assume that we know all kinds of relevant facts about naturals, integers, rationals. I'm also going to claim here that although we have not yet introduced the real numbers, it will turn out to be that the real numbers with its associated ordering relation will also be an example of a poset. Now, it's worth pointing out that the axioms of a poset don't tell you which direction the relation points in. Sure looks like it because of the sort of curly less than or equal to symbol that we use, but really no axiom says that the relation couldn't also point in the other direction. So if you check all the axioms, this natural numbers with the greater than or equal to symbol also satisfies the poset axioms. I wanted to just throw out a quick trivial example. Sometimes those are nice for just sort of seeing the boundaries of what things technically count, even though it's not usually what we have in mind when we think about a poset. But if you take any non-empty set X and you put it together with the relation of equality, right? So two things are related if and only if they are equal to each other. So really just everything is only related to itself. Well, technically that actually satisfies the axioms of a poset. Okay, of course, reflexivity is trivially satisfied because everything is equal to itself. Let's think about antisymmetry. So if the relation holds between A and B, and that just means that A equals B, and then it also holds in the other way around, which we know with equality that doesn't really tell us anything new, but okay, if we assume that those two things hold, does it follow that A equals B? Well, yes, trivially. So it is antisymmetric. And finally, it is transitive, which you can check easily. So this also forms an example of a poset, even though it's a very strange example and not at all what we tend to imagine when we think of a poset. Now, somewhat clearly, the poset axioms are meant to capture the notion of something like less than or equal to. And so if we instead think about the strict less than relation, it seems like that should not be a poset, right? And so you should go ahead and pause the video and think, well, but why is that not a poset? Exactly which axiom or axioms are violated by this example? And assuming you've had time to pause and think for yourself and come up with your own answer, I'll go ahead and tell you it's the reflexivity axiom that is violated by this example. That's what makes strict less than not a poset on this number set, but also on any other number set. Okay, let's now look at some more abstract examples. And so to get just a really dry, basic abstract example, let's take the set ABC. And let's construct completely abstractly a relation on it. I'll go ahead and write that relation as less than or equal to, and so you can see what I'm doing here to construct this relation is I am just building in right from the start reflexivity, right? Everything is related to itself, right? Everything we could say maybe preseeks itself. That's baked in by putting all of these pairs AA and pair BB and pair CC. Now, I could stop there. And if I did stop there, that actually would be the example of a set equipped with equality. But just for variety's sake, I go ahead and throw in a few more things, right? A preseeks B, and also B preseeks C. So I have those two things. Now, if I do that, which I didn't, again, I didn't have to, but just for demonstration purposes, I put those in. Then transitivity would demand that I also put in A preseeks C. And if one wants to sort of think about anti-symmetry and how one can see in this example the anti-symmetry, it is the fact that, okay, yes, everything does relate to itself. That's part of what anti-symmetry permits. But also, you never see an element pointing, right, a preseek pointing in one direction and also pointing in the other direction. So for instance, you do not observe B comma A, because if you did, then it would have to, right, these two together would have to imply that A equals B. But certainly, given how we are talking about this, we are assuming that A is not equal to B. So as soon as you put A, B in, you cannot also put BA in. Whereas on the other hand, because of reflexivity, we have to have B comma B. But if you think, okay, so with B comma B, think about how anti-symmetry sort of interacts with this, right? You have an element relating to another element, right? So, you could almost basically think that when we talk about A preseek B, well, that maybe A and B are bad choices. But in any case, think about anti-symmetry, but applied to B comma B, where the relation does hold in one direction for B comma B. It also holds in the reverse relation, which again is B comma B. But in order to satisfy anti-symmetry, we require that B is equal to B, but that's okay, right? Because here we, of course, B is equal to B. So, that kind of shows you. I hope that's not too sort of unclear how I said that, but the requirement of anti-symmetry kind of says it's okay for something to relate to itself, but it's not okay for distinct elements, right, to relate in both directions. So I hope that's somewhat clear. But anyway, okay, let's move on to talk about another and possibly more interesting example, which is suppose that our set X is actually a system of sets. And in particular, I'm just going to take the power set of the set A comma B comma C, meaning that this thing contains all of the subsets. So, should I write out all of them? I don't know. Well, I think I'm going to rely on this being somewhat familiar from a discrete math class, so I'll only write out a few of them. But so here I've written out all the subsets with 0 elements, all the subsets with 1 element, all the subsets with 2 elements, and so on. And, in general, at the end, you should see that there are 8 subsets in this system of subsets. So that's our example. That's just X. And then we're going to make an ordering on this. And again, right, I'm going to use this sort of format where I write the abstract thing on the left and the particular application on the right. So here we're taking the precedence relation to be the subset relation. So each one of these is a subset of the set ABC, right? But also, don't get that notion of subset confused with this relation, where we're also going to talk about the the set A being a subset or not of other things here. So for instance, A is a subset of AB, but it is not a subset of, let's say, B by itself. So, this fact right here would tell us that A precedes AB, but this right here tells us that the set of A does not precede the set of B. So that's an example of a poset, right? So you should check that this relation on this example makes it into a poset. Why is it a poset? Well, let's think about reflexivity. Is everything a subset of itself? Yes, so it's reflexive. What about antisymmetry? If, let's say, a set Y is a subset of another set Z, and also Z is a subset of Y, does it follow that Y is equal to Z? Yes, it does. That is famously a very important property of sets, so it satisfies antisymmetry. And then finally, what about transitivity? So if, let's say, I don't know, A is a subset of B and B is a subset of C, does it follow that A is a subset of C? Yes, it does. So the relation is transitive, and so it has all of the properties needed for an example of a poset. Okay, so let's move on and let's just briefly introduce the notion of a strict order, and it's sort of defined off the back of our notion of a sort of partial order. So we define the strict order, so that's strict precedence, let's say, in the following way. For any two elements A and B, they are in the strict precedence relation if and only if they are in the weak precedence relation, which is to say preseq, and also are not equal to each other. So basically the definition of strict precedence is weak precedence together with not a equality. But okay, so let's now move on to a new sort of structure. And to motivate it, let's again think about this example where our set in question is actually a system of subsets. So we'll take the set of ABC, and the system of subsets would be the set of all subsets of that. And then again, right, where I'm just kind of repeating that previous example where they are ordered by set, inclusion, the subset relation. And notice that in that example, some two elements may be what we call incommensurable, right? So the set of just A does not preseq the set of just B, nor does the set of just B preseq the set of just A. And so we would say that since neither relation, right, they are not in any way relative to each other by this relation, so we would say that those elements, right, the element here is the set of A, and the other element, right, these are elements in the system of sets. These elements are incommensurable. Now, when we go on to talk about the ordering relation on the real numbers, that's not a property of the ordering on real numbers. So we don't want that, right? So basically what I'm getting at is the notion of poset, although useful, is not strong enough to capture what we want for the real numbers. And so we're going to introduce this stronger notion of a total order, and the definition is below. So suppose that we have something which satisfies all of the poset axioms, right? So we're going to imagine that this preseq relation is reflexive, antisymmetric, transitive, if moreover every two elements are commensurable, right? That is to say not incommensurable. But here, let's just spell that out even more explicitly. So what we're going to say is if any two elements must relate in one direction or the other, right? That is sort of the property of totality. And so if this preseq relation, right, this partial order is moreover total, then we call it a total order. And And then we will call the pair of them, right, the set together with the relation, we'll call that a totally ordered set. So the examples and non-examples, I think, will be pretty straightforward. Any of the number examples that we've discussed, those will be total orders. And I think here, actually, I've not written this correctly, so ignore what's here. But basically, the non-example is going to be, you know, where you have the power set of some set. Maybe, what do we want to call this set? Maybe the set A. That will be our set X. And when it is ordered by the set inclusion, right, the subset relation, then so long as the set A has at least two elements, then this will always form a partial order, but not a total order. So that's the non-example. So let's move on to some exercises. And for our first exercise, we'll just take this abstract set of A comma B, and your task is to find every partial order on the set, and then of the ones that you found, decide which of them are total orders. Next, we'll prove some familiar facts about the strict precedence relation. So show that this relation is irreflexive, which is to say that nothing relates to itself that's stronger than merely not being reflexive, right? This is actually saying that everything does not relate to itself. So that's irreflexive. Show that the precedence, the strict precedence relation has that property. Show that it is asymmetric, which is a stronger property than antisymmetric. It says that if the relation holds in one direction, then it must not hold in the reverse direction. And moreover, that it is transitive. Okay, next we are going to do an exercise studying some more about sort of this strict precedence relation. Now, we are familiar with the fact that in the real numbers, if you have A is not less than B, this is essentially equivalent to B being greater than or equal to A. And the question is, does that hold generally for any poset? And so the answer is no. But your exercise is to explain why not. Why is that not true in a poset, but it is true in a totally ordered set? And so you are to both, to basically explain both, right? Explain why is it not true in a general poset, but it is true in a general totally ordered set. Okay. Next, we're going to see another example of ordering a set, right? Just to show some variety to what a poset can be. And so we have this set. I could have chosen all natural numbers, but we could just work with the set X here. Being the numbers 1 to 7, why not? And they'll be ordered by divisibility. So a number preseeks another number if and only if it divides that other number. And so your task is to show that this is a poset, but not a totally ordered set. I do want to just end the video with a remark to invite you to leave any questions if anything here was confusing, or if relevant sections of the textbook are confusing, leave a comment down below. And if I can address it in the comments, I might. And if I have time to make a video and it's a more substantial question, then I might include an extra video to address questions.